Hey guys, this is Professor Janacek. I want to go over some physical applications. I'd like to show you where some of these formulas come from. So to begin with, let's let rho of x be the density. So just so you know, this here is the Greek letter rho. It looks kind of like a P with the tail of the P being more like a J. But it's not a P, it's not a lowercase p, it's actually the Greek letter rho, and it is a function that describes the density. So let's let rho of x be the density over the interval from a to b within subintervals of width delta x and the ith subinterval containing the point x sub I star. Now all of this is to allow us to build a Riemann sum, which allows us to transition to an integral. Now, if this doesn't make sense, if that language is confusing to you, go back and look at the definition of an integral, not the antiderivative specifically, and not the fundamental theorem of calculus, but how did you build an integral using Riemann sums? That's where all this language comes from. If at this point, though, you don't remember that language or you kind of remember it, but it's not quite clear, that's okay. You can still get through this lesson and completely understand everything that we're going to talk about today without fully understanding that Riemann sum. But it's a really good thing for you to understand at this point. So make sure you know what that is, how the integral is defined. Okay, so we're going to start with some formulas that hopefully you already know, and then we're going to build on those. So the first one I hope you've seen before is the definition for mass. Mass is density times volume. You'll notice that I'm using lowercase m for mass. Lowercase m for mass. Density we already defined, we already denote using rho, and volume is uppercase V, not lowercase v. Lowercase v is usually for velocity, although some people say that velocity is denoted by the Greek letter nu, but it turns out the Greek letter lowercase nu looks like lowercase v. Okay, so again we have mass is density times volume. But volume in a rectangular sense is length times width times height. I'm going to say instead of height because that might get a little more confusing at the bottom of the page. Instead of height, I'm going to say thickness. So volume is length times width times thickness. However, if we're looking at a one-dimensional object, so rather than length, width, and height, or length, width, and thickness, we only have one of those dimensions. I'll call that one dimension thickness. So it turns out that length and width kind of go away, become one, if you will. Then we end up with mass is density times thickness. And that's where we get our formula. M equals the integral from a to b of our density function, rho of x, times the thickness, which is our differential dx. So in this case, our thickness is represented by dx. And you'll see that's very common throughout this whole lesson, that our thickness is our differential. And there you go. That's our first formula. Moving on, we have work is force times distance. This is one you should have seen. Again, work, W is for work, uppercase F is for force, and lowercase d is for distance. And just straight off this, work, force is equal to force times distance. You can see our formula. W is the integral of force, which is uppercase F of x, and then the distance in this case is our delta, our dx, our differential. So x is the distance, dx is really the change in that distance. Okay, so if you don't remember that, this is the change in the distance. And that's what allows me to use that there. Okay, so let's see. Oops, let's just do it this way. All right, so okay, we have a formula now for work. Moving on, let's take a look at force. This one again, you should have seen. Force is equal to mass times acceleration. F is equal to ma. Notice I'm using, again, lowercase m for mass and lowercase a for acceleration, of course, uppercase F for force. Now, the mass we've seen from above, mass is density, oops, actually we know even more than that. Well, no, that's the one we want. Mass is density times volume. So mass is density times volume. We still have acceleration there at the back. Now volume, I'm going to write as area times thickness. Now typically we think of volume as length times width times height in a rectangular sense, but the area is length times width, and the height, I'm going to call that thickness. So that's what our volume is. Next thing I'm going to do is just reorder this. I'm going to commute some of these terms because I know the formula that we're going to be building here in a bit. I'm just going to move acceleration rather than putting it there at the back. I'm going to move it right after density. Otherwise, everything else is there. Just changing the order. Now, going back to what we had before, work is force times distance. I just reiterate that here. Work is force times distance. But we just learned that force now is equal to this whole mess, density, acceleration, area, and thickness. So that gives us that work is, so force now is density, acceleration, area, and thickness. And of course, distance is still there at the end on that work equation. Last but not least, again, I'm going to just reorder some things. I'm going to put thickness to the back, and that just means distance is second to last here in this list of things. So again, just a quick little commuting of some terms. And there we go. We have work is density times acceleration times area times thickness. So work is the integral from A to B of density, that's rho, times acceleration. Our acceleration is going to be due to gravity, so we're going to use g there. Area is going to be a function of y, and distance is also a function of y, and then our thickness is a y value. So you'll notice I denote all of that here. Acceleration due to gravity, y is our vertical distance, so that's going to be our thickness, and area and distance are functions of y. So that's where this whole thing comes from. Rho times g times a of y times d of y dy. There you go. There's our formula for work. And then here at the end, finally, our force. Force, we saw up here, force is equal to density times acceleration times area times thickness. And I've just reiterated that here. Force is density, acceleration, area, thickness. But then area, in a rectangular sense, area is length times width. And that's all we need in order to get our force equation. So force is the integral from A to B of our density, which is denoted by rho, times acceleration, again due to gravity, so I'll denote that g. Now our length is b minus y. So that b minus y is the kind of the depth of our of what's going on here. And then, so where were we? Density, gravity, length is b minus y, width is a function of y, and then our thickness there is our differential dy. So again, this is for the situation where acceleration is due to gravity, y is the vertical distance, and we're specifically looking here at fluids lifted over an interval. And then I want you to take note that the b minus y, that is going to be the depth. So b minus y is really our length, which is the depth of this fluid. And then this value, this is a nice little thing here at the end. This value, this is a little extra. Rho times g times b minus y is referred to as the hydrostatic pressure. This is the pressure of water at rest. So nice little extra definition here, hydrostatic pressure. And there you go, that gives us the formulas. So things that you should have already known before we started this is mass is equal to density times volume, work is equal to force times distance, and force is equal to mass times acceleration. But the new things, and if you don't remember where these come from, I get it. A lot of times at this point, when you're just seeing these, I just want to memorize the formulas. You can do that. Here are the things to memorize. That would be that formula for mass. We have actually formula for work. And then we actually have a formula for work for lifting. So this is for lifting. And then we also have a formula for force. And this is for lifting. Specifically, we're looking at lifting a fluid. And those are things, if you want to just sit down and memorize, you can, but I just wanted you to see where they came from, so hopefully it'll make a little more sense. Enjoy!